So, good afternoon. So let's start, please. So, it's a pleasure to be here today at the Institut of Studies Catalans attending this magnificent colloquium by the CRM by Professor Terence Tao as part of the conference Fluid Dynamic, Geometry and Computer Science in Interaction organized by the CRM, UPC and IEC. And I would like to extend my gratitude to the organizing committee, particularly to Professor Eva Miranda, for the opportunity given to us, the Catalan Mathematical Society, to collaborate in these activities, which de facto acts as the opening session also for our society. So, thank you. So now I'm going to introduce a special speaker. So Pierre Berger is Director of Research in Fundamental Mathematics of CNRS at Sorbonne University in Paris. He's currently leading an European Research Council project in pure mathematics with the aim to show the richness and the complexity of typical dynamical systems. His work provides evidence that the behavior of typical wild dynamical systems is challenging to describe even with the statistical methods. And his research spans differentiable, holomorphic, symplectic, and fluid dynamics. In addition to his work in mathematics, Pierre is also a multimedia artist. He explored the intersection of pure mathematics, numerical simulations, and the arts, creating platforms to evoke sensations sparked with encounters with contemporary mathematical universe, what is very interesting also to make mathematics close to society. He has organized international art science exhibition focused on contemporary mathematics, and today you can get a glimpse on his through the exhibition and the talk, because we now will have the pleasure of hearing him speak in his fascinating topic, wild dynamics of light. So please.
Thank you very much. Thank you very much. So, it's late, so I'm going to start with an experiment which might sound to you familiar. So we are going to take a cat and put it in a box, and we put some mirror on the wall of the box. Okay, and so the questions is, what does the cat see? So you just have to imagine you put a box, like mirror on each of the sides of the box, and what does he see? So, I mean, the answer is quite easy. I mean, he sees nothing. There is no light. I mean, so like I ask these questions to those departments like nearby mine, and say like, I got this problem. I say, yeah, it sounds to an experiment that somebody did a long time ago. So you just have to put some stones which emit light inside the box. So, okay, I did this, and that's what he sees. Maybe you can lower the light. It's possible to lower the light because we don't see anything. Okay, thank you. That's perfect. We can continue like this. So that's what does the cat see. So you can see this. That's interesting. So like they asked me, you can stay like this. I think it's nice. So like they asked me to, like, we can now try to understand this image. And so like like in classical optics, I mean, if you want to understand the image, you have this cat, and what he can see, actually, is its image that we call a virtual cat, okay? And what he sees is exactly that the thing that you will see if you send a beam of light, and it reflects, but it continues, and like see the symmetry of this cat about this mirror, okay? And you got the same thing like in front of him, on the right-hand side of him. And you can play this game also like in diagonal. I mean, like you can do 2 bounds. And so you got also an image, a virtual cat here, and you can continue so on, like this, to play this game, and you got a landscape of cats, okay? And like, that's exactly what the cats see, actually. We understand it, and we can recognize some pattern, okay? So you can see, actually, that you got a tilling by cat, and like you get exactly this pattern, which is done by translation. So if I want just to talk to mathematician, like graduate mathematician, I would say that the cat live actually on a torus, on a 2 torus, or a 3-dimensional torus, okay? So what he see is basically what he see if you glue this side to that side, like if I glue this wall to that other wall, and the light pass through that wall to go back to the other wall, okay? That's the same thing. Okay, so far so good. We can go higher in the complexity and do the second experience. So now you deform the mirror, okay? You just do the deformation of the mirror, so the mirror are still perfect, but they are not plan, okay? And so what does the cat see? So like it depends of the deformation of the mirror, of course, so we should decompose, like split the experiment, and have the first mirror, which is straight, like the same as before, a mirror which is slightly deformed, another one which is much more deformed, okay? And here are maybe you can switch off the light. You have the first image, which is like this, and then you got more deformations, and again more deformations, and again deformation, okay? And so, like this image, which is given to this, is given actually by the orbit of the light. I mean, like the path of the light, okay? So, yes, okay, so here, and here. Okay, so again, it looks like familiar. I mean, it's something like you might have seen if you look at yourself in the water, but you have moreover another water above you on the left-hand side and so on. Okay, so let us study this experience and introduce actually the dynamical system of the beam of light. Okay, so what's happening? So you got the beam of light, which is reflected on the wall, and at an angle, and you can just put the position of the hitting point on the wall, and look at the angle that you have, and go after this one more time, and you have this reflection law, I mean, like, which is you arrive with an angle, and the angle at the end is the same, and you continue straight, okay? And you do this one more time, second time, and so on, okay? And this is what we call the orbit, okay? You get a sequence, and like the visualization, like the landscape we saw just before, is given by that dynamic of beam of light, okay? And so, what can we say about that dynamics, okay, a priori? Like we have a well-defined system, like what can we say about this? I'm going to see we cannot say a lot, but I mean, at least we can say something, is that there is a very old theorem, and which is called Poincaré recurrence theorem, okay. So what's going on? Like when we have this dynamic of light, actually we are working on Hamiltonian dynamics, okay? Like the reflection law that we have for the bonds is like you are just throwing, it's like the same as you were throwing a ball, a perfectly elastic ball, and so you preserve the energy and you preserve the Liouville form, okay? So like in particular, you have a volume form which is preserved, and so you can apply this theorem, which says the following thing, is that almost every orbit, okay, is recurrent. In practical, this means that if you take for almost every initial data, okay, like the point on the wall and the angle, if you wait sufficiently long, you will be arbitrarily close, you will go back arbitrarily close to yourself, okay? So an immediate corollary of this is that the cat can see himself almost everywhere, also Yellowstone. And why you have this? Because if you look at in one direction, I mean, you know that these bonds, like these light bonds, will go back to his eyes, and so he will hit his head. Or he will hit something else before, which is Yellowstone. Okay, so like that's a non-trivial consequence. I mean, if you would like to prove this fact, this corollary without that, I think it's very complicated. Okay, so what else? I mean, So like, and indeed, you can see that like the horizon is full. I mean, it's yellow, or you can see him everywhere. Okay, this is the evidence. Okay, so like now, let us go one step further. And like when you see this, I mean, it looks like the motion of the light is somehow random. Okay, like it starts here, it rebounds here, it goes there and there. And like what you could wonder is, okay, like if you start to add somehow like a random noise everywhere, maybe like the orbit, this orbit is going to go everywhere in the square and hit all the wall everywhere. And that's kind of a natural statement, I mean, and it's a very old statement, which goes back to Boltzmann, and which is called the ergodic hypothesis. So you got a system which is Hamiltonian, and what Boltzmann states, and then what Birkhoff and Koopman formalize in the modern language of probability, and also Poincaré did in a more topological way, is that actually almost every orbit is going to be equidistributed in the same level, in the same energy level. Okay, so like which means that if you look at this orbit, it's going to go everywhere at every angle, typically at the beginning. Okay, so that's the ergodic hypothesis, and actually this ergodic hypothesis is completely wrong. I mean, it's true, but it's wrong. Both. I mean, depend. So, like the origin of this assumption is you work with gas, okay, and you put some water, for instance, in a cube, and you will look at the motion of all the molecules of water, and they are going to have a motion like this, and this is an Hamiltonian system, okay. I mean, you can approximate this by an Hamiltonian system, and like what the conjecture was, the hypothesis was that all of the particles will go everywhere, and will have all the positions possible. Okay, that's and each of the particles will have the same state in average by the end. So, like you can check it in particle. You put a barometer in this room, and it will be the same pressure as this one, and it will be the stabilized pressure. It means that the particle of the water will converge, like the force that exerts as a pressure will converge in average, and you can see this. Okay. But on the other hand, like if you look at the sky, for instance, you will see non-homogeneous sky. I mean, perhaps today it was gray, but just before it wasn't gray, it was blue. You can have clouds, and you can be not very convinced with this argument, but you can then look at other planets' sky, like Jupiter, and you have this atmosphere that you can see around, which could be, I think, modelized as a Hamiltonian system. It's almost a perfect fluid at this scale. And you see that you got some regions which are darker than others, and this doesn't mix. Okay, so this is one example of a system which do not look like ergodic, and which is rather Hamiltonian. And in case you're not convinced by this experiment, you can look at this one, which actually is a modelization of the light of the cat room. Okay, so we're going to understand what does this picture mean. But what we can see already is that we've got some regions which are not connected to each other. Okay, so let me try to explain you this kind of simulation about the cat room. Okay, so we start with a modelization with the light in a square, okay, with a flat wall, and we saw just before that we could actually work on a torus, okay, where we identify the wall, the opposite wall. So when you got a beam of light which go to one wall, then it go back to the opposite wall with the same angle, okay, here to here, and what the position it hit above, which is identified to below, is by a triangular geometry, like elementary one, is equal to S naught plus the tangent of the angle that we had here. Okay, that's like elementary trigonometry. And like if you look at this, then you have identified this point to that point. So like this segment actually is a circle. Okay, you glue the two ends of this segment, and so you are here on a segment, and here you have your angle, which are between minus pi over 2 to pi over 2, and you we are twisting, okay? Like this is a twist. Like this function is increasing. It's just an increasing function. So your dynamic here is increasing, okay? So that's the modelization for the first experiment. I mean, it's not even, it's a perfect modelization. And what we know for the second experiment is that we have exactly the same thing plus a perturbation, right? I'm not cheating about this. And now I would like to modelize, and I would like to do some experiment, like numerical experiment, to show you the dynamic of this. And this function is kind of tricky, you know, like it goes to the infinity pi over 2. You don't want to deal with this. But actually, like it is conjugated to like if I just had a theta node. I mean, it's the same thing because you can just rescale and you get exactly the same dynamic. So we can deal with this. And this is a first experience that we can do. We can just play with this perturbation of the dynamics. And we have another experiment that we have, like just before, like a transcendental function, like the tangent function, and I can just change it to another one, which is sinus of theta, which is also a transcendental function, and look at what's going to happen. And then I add a perturbation. So to be very concrete with you, I'm going to add two kinds of perturbation. I'm going to add this perturbation, like a sinus of this function. And here I just choose like numbers like this, like just for fun. I mean, just random numbers, just to show you that what I'm going to show you is actually really what you have in the nature of symplectic dynamics. Okay, so like this is those two maps are Hamiltonians, and you have here epsilon, which measures the perturbation. So when epsilon is equal to 0, you got the original model. If you do epsilon larger, you start to go with walls which are more and more deformed. Okay, and the same thing for below. You got the epsilon below, and this is my parameter. Okay, so let's start with experiment now. So okay, so sorry, no problem. Okay, so at the beginning I told you like actually we have a shear, so all the orbits are horizontal, okay? And like here I got my wall, which is here, which is good to this wall, okay? And also what I did at this stage is I also glue the top to the bottom, okay? Just to make it simpler. Okay, and then I'm trying to, what I'm going to do is that I'm going to introduce perturbation, okay? And so if I introduce perturbation, I start to have this pattern which appear, okay? And what we see here is that we see actually a lot of line, curves, okay? We see a lot of curves, and those curves here, and black curve, and also we see a lot of circle around, okay? So there's like there are some people who say that this is the greatest achievement, like the existence of such a curve, perhaps the greatest achievement in the 20th century in dynamical systems, and those are like called Chem circle. Okay, so that's a Kolmogorov, and Kolmogorov proved actually that when you perturb a twist map, look, exactly the map we start with, you will have a lot of horizontal curve which will survive. Okay, and like a positive set, and like this set is going to be of high measure. Okay. And what it also proves is that when we have a fixed point whose differential is a rotation like this one, here we have a fixed point with a rotation here, we will have also a lot of points. Okay, so that's actually something which like this picture actually is something that you can expect from theorem from the 50s. What's still amazing is that all the theorems work for actually an epsilon which is super tiny. Okay, so we should not see this, but we see this. I mean, like we are not able to prove that we see this, but we actually see this. Okay, so that's one of the aspects of this picture. Another aspect of this picture is this point that we have here, which is a hyperbolic fixed point. So this is a fixed point. The map is sent to itself. Okay, and if I put it at the center, you can compute the differential of the mapping here, and the eigenvalue of this differential will not have eigenvalue of modulus 1. It will be conservative, so the determinant will be 1, but will have one eigenvalue smaller than 1 and one greater than 1. And what you can do, what you can prove is that you have two curves here and here, whose backward and forward orbit will converge to this one. So this curve will have its forward orbit will be converged to the fixed point, and this curve will be made by a point whose backward orbit will converge to this point.
Sorry, what did you say before? That you see it for the theorem gives it for the small epsilon, but you see numerically for large epsilon, or what did you say?
Yeah, exactly this. Like the theorem is valid for small epsilon, but we still see it for large epsilon. Exactly. And so like this is invariant, okay? And so what you can do is that you can iterate it by the dynamic, okay? So let me do this. So I start to iterate this by the dynamic. So I look at as a backward image, and if I iterate this, it starts to snap like a snake, okay? And it continues to iterate, and you have like this beautiful and amazing pattern, okay? And you can continue so on. And like this pattern that you see, actually it's beautiful, but it's extremely complex. And we don't have any tools in geometry nowadays to describe the geometry of this. Okay, it's an open problem to just say what it is. It's an open problem to say if like the geometry of this tangle, like we call this homoclinic tangle, has a closure with positive measure, for instance. We don't know this. And like what we suspect is that like we should have an instability region, like all the points in this tangle show instability and exponential instability if you look at the future. And we expect, like some people expect, that actually for a set of positive measure of points, like with positive probability, if you take a random point on the screen, you should have your differential which go exponentially fast to the infinity. So if you want to check this for the n first, like 400 first iterates, you arrive with, you arrive to this picture, like this. Okay, so this is the yellow part. And the yellow part, so if I center again, is this one, okay? And it coincides more or less with this one. Okay? You can see.
Here, and this one will be the color code here. I understand that there is a game.
Okay, the color code here is a Lyapunov exponent, to be direct. Okay? Lyapunov exponent. So the exponential growth of the rate of exponential growth of the derivative. Okay, so that's it. I mean, so we got CAM, we got this, and actually this is all what we know about unconservative dynamic. I mean, not all, but almost all what we know. I shouldn't be recorded saying this for the colleague, it's bad. Still, I miss a lot of things, of course, but I mean, like, basically, like this, I'm showing like the two main phenomena that we are working on. Okay, so I promise you to show you another experiment, and this is another one. This was the sinus function, and actually we got the same thing, but you can see that it's more complex, and you can see also it's not ergodic at all. You got a lot of little objects here, look like a galaxy. It's amazing. Like the complexity is amazing. It's I mean like a conservative dynamic do produce fantastic pictures, and you can see here, like we suspect here to have an invariant curve which are Meandrian. You got here an elliptic point, here another elliptic point. Here you got also a stochastic C, like a positive Lyapunov exponent a priori, which are here. We should have also a lot of CAM circle everywhere, and we also have like a homoclinic tangle here that we can see here, which are around. And this is the landscape that we have in symplectic two-dimensional dynamics. Okay, so then what you can wonder is like, okay, so what's going on with the statistical behavior of my points? Okay, so I'm going to do another experiment with you, and now I do the following thing. I take a point on my torus, I take one of those dynamics, and I look at the point, okay, and I see what is going to be its orbit, and I see that the orbit of this point is going to move, to have different stuff. I mean, you don't see something which is ergodic at all, okay? You got a lot of CAM circle, attractors, and so on. And, well, so, I mean, like, to describe this, the union, the space of all the attractors that you can have, all the accumulation, all the orbits that you can have is huge. It's something like whose complexity sounds interesting. Okay, so another thing that I would like to do with you is that I would like to don't be cheating. Okay, like we were working at the beginning. We were working with a three-dimensional torus, right? Like the cat was in a box, was not in a square, and so the walls are two-dimensional and the angle also. And so actually we were working with four-dimensional dynamics. Okay, so I should represent to you a four-dimensional dynamics, but that's complicated, right? Like to show you a four-dimensional. But actually there is a way. I mean, this is the same way that you do. When you want to see a baby in the pregnant woman, you can use ultrasound and cut the body of the person with a plan and look at what's going on inside it, right? And then you can change the position of the plan. Okay, so let's do this in a four-dimensional space. So here we are. So my pointer is moving, and I'm moving the plan here. And what we can see is that it's not ergodic. I mean, we have different color. Okay, so each of the color are different part of the dynamics. And if I start to look at this, I mean, I see a lot of points, and so now I had to look at where I want to go. So let me see. So if I mean, this is the same process. Okay, so at the top left, you can see stuff here. And what's going on? So like if you are in a, so you don't see curves, you just see points. So why? Because in dimension 4, actually the cam tori are two-dimensional, and my plane is two-dimensional, and so if I intersect the plan with a plan in dimension 4, I got a point. Okay, so I got a cloud of points everywhere, and what I can see is that actually I can see arithmetic conditions sometimes, which are given by the Diophantine condition given by the theorem of Cam. Okay, so sorry for these hard words, but that's.
Program this kind of scan situation?
With my hand. Okay.
I wanted to see it.
So the code is on the right hand side, is here. Okay, so let me go back to this. So we did this experience, and now what we like the question that we can ask. I mean, there was this positive entropy conjecture, which is one of the main conjecture in our field. But you can ask a more sober conjecture, like a questions, is whether actually you can have ergodic subset, like set where the orbits are going to be equidistributed, of positive measure, which are going to happen typically. And this is we don't know. We don't know at all. It's completely open as a question. Okay, so that's a question. Like we actually do have examples that we can do analytically in the conservative world, but like those examples that we have for now are given by surgery of annals of mapping, and so like they are very special. And this is this. So you can show that they appear densely in the space of dynamical systems, but they are very fragile. I mean, you can break them with a very little perturbation. I mean, this is like you got those two curves that I showed before, which coincide, and this is very fragile. Another possibility to have an ergodic subset of positive measure is to do what is called pseudo-rotation. So this can be done also in analytic and conservative, but it's very fragile. I mean, if you do a little perturbation, they will blow up. Okay, so actually, like we have one hand where we have wonderful pictures that we don't understand. On the other hand, we got theories that we are not very much able to apply. Okay, so in conclusion, I would say that many systems are non-ergodic, as we saw in the experiment, and so what interests me as a question is actually will it be possible to show that the statistical behavior is so various, like we have so many ways of statistical behaviors that actually it's not possible to modelize them by statistic, like by the straight use of statistic. Okay, that's the question. And another one, which is more poetic to finish this session, is it possible that a very simple expression of dynamical system, as I showed you just before, can produce as much complexity as we see in the nature? So thank you.